What the architect wanted to do was replicate the steel riveted plating of the hull of a battleship in the image of the walls and the soffit of Westminster Station. So let's go over to a section of the wall now. The mix for the concrete was specified with a mica sand, which creates this sparkle effect. It's probably not easy to see here, but when the light's shining on it, the mica sparkles. So you've got the grey appearance of the concrete, which replicates the steel plate. If we look here, you can see this rectangular pattern of the concrete. Now that rectangular pattern is supposed to replicate a piece of steel plate of the battleship. And if you look closely, if you come over here, see these nodules. This is to replicate the riveting of the steel plate. Now, to form this in concrete, the architects produce drawings identifying where every panel was to be placed. And this drove our carpenters mad when they had to exactly replicate the shutters for the concrete. And these nodules were formed by countersinking the nail holes into the plywood. So if you imagine a little countersunk hole, when you pour the concrete, it fills the hole, and you end up, once the formwork is stripped, you end up seeing these. This ticket hall runs diagonally through the site, and below us here is 30-metre deep excavation, and the excavation was done underneath the operational railway of the original District and Circle line. So imagine, how on earth do we excavate below this operational station? Well, that's one of the major challenges we had. Now this shape of the supports of the ceilings is called a diagrid. And this had not been done before, because you can see from where the columns are, this soffit is spanning quite a wide distance. But structural calculations were done, identifying the amount of reinforcement that had to be incorporated. But to have confidence that it was working structurally, a scale model was created in concrete. I can't remember, I think it was a half-size model of a particular section supported by 4 table legs, replicating the diagrid, and it was loaded and monitored, and that gave the structural engineer the confidence that they had the right amount of reinforcement to sustain the loads. So as we go further down, I'll show you the perimeter of the station box. Over there you can see what might be called a rough finish. That's the diaphragm walls. Now, the diaphragm walls were constructed, start of construction was some 6 meters below street level. But underneath the District and Circle line platforms, the diaphragm walls were constructed within a restricted headroom, 7 meters. So we had to make specially adapted diaphragm wall rigs with a low headroom jib and a grabbing bucket to build. A few of the panels were built underneath the operational railway. If you can imagine starting excavation below this slab, and between that wall there on the south and the wall on the north, which is over here, there's a good view of the north wall. Now, the permanent design have these permanent props, which we call flying shores. Yeah. So we recognised well, why don't we build these props on the way down, incorporating the permanent works,
Right.
rather than all this temporary works, and then starting from the bottom, building our way back up.
Yeah.
And if you look at these wailings, horizontal wailings at different floor levels, and the vertical buttresses,
Yeah.
they're essentially providing extra stiffening to the diaphragm walls to make the shoe box a very, very stiff box.
Oh, I see. Yeah.
So the other advantage of going top down is, as we were excavating down to each level, imagine those wailings at the different levels, we would build the buttresses and the wailings on the way down.
Right.
And from here you can more or less picture the box shape. You know, the north wall and the south wall, the west wall. Now it's shown curved there, but in reality it was square. So behind that curved shape, there's plant rooms and other facilities. And just imagine this excavation without all these escalators, and that shows you the sheer size of the box. Now, in order to demonstrate that it was structurally sound by putting these permanent props in on the way down, we had to do a lot of instrumentation and monitoring. We had strain gauges on the props monitoring its loads. We had inclinometers on the diaphragm walls monitoring any movements, and there was negligible movement because it's such a stiff structure. And there are 5 primary columns supporting this roof structure, and below one of the piles, the pile was constructed by hand mining, so it was sunk as a shaft. And so the miners went down the shaft, it was jacked down, and then from that they had 2 tunneled struts at about 40 meters below ground level. And the purpose of the tunnel struts is to strut between that wall, the north wall, and the south wall opposite Big Ben, to stop the toe of the diaphragm walls moving in. As we're in the eastbound station tunnel, this is the higher level one. So the westbound station tunnel is directly below this. And the other side of that station tunnel, you've got Big Ben. Now, these platform edge doors, it's the first time in London that platform edge doors were used. All of the other underground tunnels in London don't have platform edge doors, apart from Crossrail. So Crossrail, they're all platform edge doors, replicating what was first installed on the Jubilee line. Now you can see here that the tunnel lining is spheroidal graphite iron. Now, these station tunnels were done in 2 stages. The first stage was the tunnel borer machine coming right through here, which acted as a pilot tunnel, about 4.5 meter diameter. And then later on, once the 2 running tunnels had been constructed, one above the other, we had another shield which enlarged from the running tunnel.